The reincarnation server is pinging the disk driver, and it's not answering at some point. And so the reincarnation server says, well, in that case, I'll create a new disk driver. Furthermore, it tells the data store there's a new disk driver, and this is its endpoint. So it knows the new endpoint is a little like an IP port in the TCP/IP protocol. It's like an internal number. So when you send things, you have to give the internal address of it. So it gives the data store the internal address. So there's a mapping of disk driver is this internal thing. So the file server, and also the reincarnation server, sends a message to the file server saying, I have some sad news for you. Disk driver has passed away. I don't think we can recover the electricity. So the file server now knows that instead of getting an answer from the disk driver, it got an answer from the reincarnation server saying, ain't no disk driver anymore. And the file server says, no, that's too bad. I really like it. It's a great disk driver. All right. So it goes and asks the data store, by the way, is there another disk driver, in the neighborhood? And the data store says, yep, got a new disk driver. Good kid on the block. Just showed up here. Here's his endpoint. Great guy. So the file server then sends a message to the new disk driver saying, could you read this block for me? And the new driver says, yep, that's what I'm here for. It's in the block. And reading and writing blocks is idempotent. Right? You can give a read command as often as you want. And assuming the disk itself hasn't failed, then eventually you'll get a good one. The driver might fail multiple times in the process, but eventually you're going to get a positive acknowledgement from the driver saying, I read it correctly, the checksum was okay, here's the data. So it can fail multiple times. Likewise, if you write it and it fails, you write it again and again and again until you finally get a good write. Okay? So this process can go on indefinitely long if need be, but eventually we'll succeed and get the right result. And the user doesn't notice anything other than a possible delay while it was rebooting the driver repeatedly. The system doesn't go down. Okay? So the system is self-healing like that. And that's the property, I think, that all software should have when we're starting with operating systems. When it finds a problem with itself, it fixes itself. Okay, other drivers that can crash too. Ethernet, well, if it loses packets, no big deal. The higher levels expect that. TCP can recover from lost packets, so there's no problem at all. The printer, well, I just got to print the drop again, and let you go. And audio, you play the song again. You don't know where you were when it crashed. You just can't do anything. And so on. Okay, kernel reliability. There's a number of features that enhance kernel reliability. Well, to start with, less code means fewer bugs. 3 bugs per 1,000 lines. Less code, less bugs. Personally. It also means that there's a reduced trusted computing base. Is that part of the system that's got to work to make it work. So the kernel has to work, the file system has to work, the process manager has to work, the reincarnation server has to work, but the audio driver doesn't have to work. There can be bugs all over the place in the audio driver. It doesn't bring the system down. It brings the audio driver down. In contrast, in Windows, there's probably 10 million lines of code which can bring down the system. In Linux, there's 4 million lines of code. A random bug in the audio driver can wipe out Linux. It's a much smaller base of code that can do equipment. There's no foreign code in the kernel. That means that if you buy a FireWire card, you plug it in, they give you a CD-ROM. You put the CD-ROM into the drive. What are you doing? You're installing foreign code into your kernel. Okay. That foreign code was probably written in Taiwan by some programmer who was in a big hurry. His boss said, "We got to ship the product. Got to ship the product." The programmer didn't have time to test it. And it's going to your kernel. You don't want foreign code in your kernel, especially code that probably hasn't been tested. In Linux, there's no foreign code that ever goes in the kernel. The kernel, it's not entirely stable because we're dealing with ourselves. But you never, in the normal operation, would add code to the kernel. You add drivers. There's a user process. Okay. The data structures are also static. There's no malware. The process table is fixed size. It just makes things simpler and less likely to go, no memory leaks and that kind of stuff. So, simple way to do it. Because moving bugs to user space doesn't reduce the number of bugs, but it does reduce the power the bugs have to cause damage. So it's very important. Now, when you get all these components, there's inter-process communication between the components, and there are a lot of issues there. We have fixed length messages. There's a header file which defines the message as a union of a number of typed messages. It's the largest of those. In the Intel architecture, it's 36 bytes. And there's no buffer overrun. You can say send message. You say send it to him, and here's the pointer to it. But there's no length field. It's a global constant. And so there's no danger that you'll give the wrong size because the size is a global constant. The rendezvous system says when the sender and the receiver are both ready to go, the data is copied over, but not until. So there's no buffering. It doesn't go into a buffer pool or something like that. which makes it more complicated. So you don't lose messages, you can't run out of buffers. It's much simpler to have this rendezvous scheme where you just wait until both the sender and receiver are ready to dance, and then you do it. Interrupts and messages are unified. Interrupts are a pain in the wazoo. You want to turn them into messages as fast as you can at the very, very bottom. So a driver just says, get message, receive. And it gets a message from the hardware saying basically there's an interrupt. So they're integrated into the same framework. Drivers are the enemy. Drivers are untrusted code. We assume that they're hostile. We probably assume they're malicious, and you've got to worry about management. Okay? Bugs and viruses have been. We've gone to some effort to make it hard for them to spread. If they infect one, they can't touch the kernel data structures. They can't wipe out the process table. They can't change the MMU. They can't do any of that stuff. If it's a bad pointer, the driver will crash. But it doesn't bring down the system. It just brings down the driver. Likewise, an infinite loop will hang the driver until the reincarnation server notices that the driver is hung. It doesn't bring the system down. So they have very restricted power to do damage because they're not super users. Now, why don't people make drivers in kernel mode at all? Well, there's some things drivers have to do to get their work done. And we call these the 7 deadly powers. So every driver has a policy, every server, listing its powers. And it's a kernel data structure. The kernel knows what this driver is allowed to do. You can imagine drivers coming shrink-wrapped with their policy statements cryptographically signed by the vendor or whatever. The administrator makes them. It's a little bit open question how you do that. But what are the powers that drivers and servers sometimes need? Well, one is to execute protected instructions. There's special instructions on the hardware to change from user mode to kernel mode or something. Drivers can't do that. If they need to execute one of these peculiar instructions, like something which is not allowed for user programs, they got to ask the kernel to do it for them. The kernel has this API which allows you to do special things. If it isn't exported by the kernel API, you can't do it. Memory access. Drivers need to touch memory to copy things to and from user space. You can't do it. They have to ask the kernel to do it. And the next slide shows how that works. Device I/O. They can't do it. They got to ask the kernel, hey, go read this I/O port, go write this I/O port. DMA. That's a real problem. Many cards can do DMA. They can write all over memory. There's no way to stop it unless you have an I/O MMU. Most current PCs don't have it. They're starting to happen. We have one from AMD which has got an I/O MMU. It's like a regular MMU only for the I/O. So all the I/O has to go through the I/O MMU, and then you can limit it. So we've got the code to run with an I/O MMU. The hardware isn't there quite yet, but it's coming down the road, next generation of I/O MMU, so we can stop the road with DMA. IPC. You don't want to be able to send a message to anybody because you might not be expecting it. There's a bitmap for every process saying what processes this process may communicate with. Bits. Whenever you try to send to somebody, the kernel checks, is this an allowed target? If so, do it. If not, report back protection violation. Kernel calls. This is 35 or so kernel calls. So if an audio driver is taken over by a virus and it tries to fork off a shell, the first thing it does is the low-level call to create a new process. There's no fork type call. What happens, it gets back an answer saying, protection violation, you're not allowed to fork. You don't have that power. So not every process can do every kernel call. It's a bitmap saying what you can do. So there's 35 or so bits allowing a process to do certain things, but not other things. And of course, the idea is to restrict every process to the absolute minimum of what it needs to do to get its work done. Okay? This is in resource loss. We try to avoid shared resources as best we can. So these are the ways we try to reduce the power of every driver and server to the absolute minimum it needs to get its work done. Okay. Memory grants. Let's say the file server needs to